My name is Flash Isaac, and I'm a teacher from the future. You are welcome to episode number 69 of the 120 Days to Jamb Physics with Flash Isaac. In this episode, we shall be looking at dispersion of light. Dispersion of light. You see, we looked at reflection, diffraction, and many other features or properties of light. This episode will focus on dispersion of light, and in the process, we shall look at color missing. We shall look at electromagnetic spectrum. We shall look at spectra and other very interesting parts. And I promise you are going to love the color missing aspect. Color missing is one of the areas that confuses students when it comes to most examinations. They will tell you that a blue light is passed through a red light. So what color is formed? You know, all these things shall be made clear right in this article. It's going to be a long class, I guess, because we have a lot to cover. Then there shall be a lot of notes and revision. Let's see what we are able to do. By the way, if you are watching this video and you've not subscribed to the Flashlearners YouTube channel, please do that immediately. Subscribe and turn on the notification bell so that anytime new videos are released, you get notification. And tell your friends about this class. It is going to help you. With this class and the Flashlearners application, you are going to do very well in your examination. So install the app on your various stores or chat me up directly if you have questions or if you want to share anything with me. And by the way, why won't you want to chat with this handsome guy? So let us begin. We've established that refraction can take place in rectangular blocks and refraction can take place in triangular prism. We also said something like this. If this is a prism, this is the surface we are concerned about, and there is an angle that is perpendicular to the surface, and we call that the normal. So this will be normal. The normal is 90 degrees to the surface we are concerned about, to the refracting surface. Now we said that if light travels from a less dense to a denser medium, it tends to bend towards the normal. So if this is light coming this way, obviously this is a medium, this is air. Let's call this air. Once it enters this place, because of difference in speed of light in different mediums, that is the reason for refraction, because light travels at different speed in different medium. And this is normal. It tends to bend towards the normal, and it goes and goes. But the details of this is not the scope of this class, because I've already treated refraction in prism and in rectangular blocks. This is where I am getting towards dispersion. Now, if this ray, this incident is light, let's say white light. When white light is passed through a triangular prism, it will split. It will split into its component colors. So, let's say this is white light. Once it is passed through this prism, it splits into its component colors. Let's do something like this, like this, like this, like this, like this. So these are the component colors of the white light. And this is the short form for these colors. It is Roy beef. This is the shortcut for the component colors that will be formed when light pass through a white light pass through a triangular prism. In summary, when white light is passed through a triangular prism, the light will split into its component colors, and that is referred to as dispersion. And these colors are Roy-Beef, where arrow is red, O is orange, Y is yellow, G is green, B is blue, I is indigo, and V is what? Violet. Violet. So now looking at this Roy-Beef, let's put it like this. Roy-Beef. ROYGBIV. The order in which the light splits is like this, going up. It is this V that splits first, which is the violet. After violet comes out fear. Indigo follows. Blue follows. Yellow follows. Orange follows. And red follows. Red is the last to come out. So in terms of the splitting, it is violet that comes out first. How about in terms of deviation? In terms of deviation, this is the normal, right? Now, if you look at this one, this is most deviated. It is the closest to the normal. While this is the least deviated, it is the farthest from the normal. So in terms of deviation, red is the least deviated and violet is the most deviated. So in terms of closeness to the normal, red is not so close, is the least close, and violet is the closest to the normal, so it is the most deviated. So red is least deviated, and we say violet is the most deviated. So which means after red is deviated, the next one is orange, the next one is yellow, green, blue, blue, indigo, and violet. So everything starts splitting from here, not from the outside. What else should you know? In terms of frequency, violet has the highest frequency, which means violet is the most powerful. In terms of frequency, red has the least frequency. Under waves, we established that frequency is inversely proportional to wavelength, which means whatever has high frequency will have low wavelength. Whatever has low frequency will have a larger wavelength. Therefore, out of all these colors, red has the largest wavelength. So least deviated, largest or biggest wavelength. It goes like this in increasing order. And violet has the least wavelength, because it has the highest frequency. If you are confused about anything so far, please start the video, because this is the basics and I'm sure I am making a lot of sense. Classification of colors. Classification refers to grouping. If you go online to search for classification of colors, you see different results. Some will say that classification of colors are primary, secondary, tertiary. Some will say primary, secondary, tertiary, and quaternary. There are a lot of things you will see. But for objective exams, now every exam has syllabus. So your syllabus or the recommended textbook, they will definitely give you what you need. Now for the sake of this class, or for this scope, these are the standard I will give you for classification of colors. I will say colors can be grouped into colors of light, colors of pigments, primary colors, and secondary colors for this scope, for this syllabus. Now look at this. Colors of lights are simply colors that are reflected by light. Now, the color the eye sees is the color that an object reflects. When you see a white color, it means that object is reflecting all the colors of the white light, which means Rooiwave. So once all the colors are reflected, you see a white color. Now, if some of the colors are absorbed and others are reflected, you see a particular color. You'll see that soon under color missing and a lot of things. I told you this class is going to be a very interesting one. Now look at this. The colors of pigments are colors that are produced or reflected other than light. These colors are not from light. If you see the petals of flowers, the colors they produce are pigments. So they are colors of pigments or colors of paint. So these colors that are reflected or colors from light are colors of light. Colors other than from light are colors of pigments. Now, primary colors are the basic colors that every other color depends on. Just like we say fundamental quantity. Quantities, which other quantities come from. Why? Secondary colors are derived colors, which means they come when you mix primary colors. When primary colors combine, they will give you secondary colors. Now, somehow, let's start preparing for color mixing. If this is primary colors, red, green, and blue, that is RGB, let's draw two charts. Let's say the first is this, is this. This is too big. Will I have a space for the other ones? Arrow O Y G B V. Don't put the I. So just write something like this: arrow O Y G B V. That is red, orange, yellow, green, blue, and violet. Our normal Rooiwave, the colors that are produced, is supposed to be IV. Skip the I. Say arrow Roy B V. Now, if all these colors are combined or all these colors are reflected, they will give us white. So we combine all these colors to give us white. But this is red, this is orange, this is yellow, this is green, this is blue, and this is violet. I will draw another chart here. Before then, when you have a chart, a pie chart, like this, what is here simply refers to what this and this have in common. What is here refers to what this and this have in common. What is here refers to what this and this have in common. So this implies that if you mix red and yellow, you are going to get orange. So red plus yellow should give you orange. What does that also mean? It means yellow and blue, yellow plus blue should give you green. This also implies that red and blue, red plus blue should give you violet. Should give you violet. If we have this, let's look at the primary colors we said. RGB. Let's say red, green, and blue. We have subtractive colors, or you say subtractive primary colors, or you can even call them secondary color or whatever. Now, the additive colors on the main primary colors are red, green, and blue. Red, green, and blue. The subtractive color, these are colors that they absorb one primary color to form another color. So, the three subtractive colors are Y, M, C. Y, M, C. Y, M, C. These are the what? Subtractive colors. Subtractive colors. What is Y? Yellow. What is M? Magenta. What is C? Cyan. So if this additive primary or normal primary are red, green, and blue, and we said that secondary colors are colors formed when you mix primary colors. So when you mix two colors and get another color, you are basically dealing with this. The new colors you are getting are obviously secondary colors. But for the case of these subtractive colors, they absorb one color out of the three primaries. So look at this. The subtractive colors, or you call them subtractive primaries, are Y, M, C. Y, M, C. What is Y? Yellow. What is M? Magenta. What is C? Cyan. So let's place them here. Y, yellow, is here. M, magenta, is here. C, cyan. Yellow, magenta, cyan. Please, there is a mix up here. This is RGB. Sorry, red, green, and blue. So apart from this face, I don't think it's not going to affect anything we've said so far. It's not going to affect anything. The primary colors remain red, green, and blue. And the subtractive colors remain YMC, yellow, magenta, and cyan. Or we say yellow, cyan, and magenta. Red, green, blue, primary, subtractive, yellow, cyan, and magenta. Yellow, magenta, and cyan. Before we proceed, there is something called complementary colors. Complementary colors. In this chart, any color that is facing each other, they are directly facing each other, are complementary. So with this, you can get a lot of things. No color missing, complementary. In fact, almost everything. If you can draw these two diagrams, you will not need to cram to understand or answer questions on that color missing. For example, the red and cyan are facing each other like this. So red and cyan are complementary. This is magenta, this is green. They are facing. So green and magenta are complementary. This is blue and this is yellow. So blue and yellow are complementary. And everything will give you white. So let us proceed. Color missing is gradually coming in and gradually getting very, very interesting. If you have something like this, ladies and gentlemen, this is what happens. I told you that the subtractive colors are yellow, magenta, and cyan. They are the subtractive colors. If you see this cyan, right, it is facing red. So cyan will absorb red color, leaving us with blue and green. This cyan absorbs red, leaving us with blue and green. So subtractive colors, they absorb one of the primary colors, leaving the other two. Now if you put a magenta color in a mixture of red, green, and blue, you see magenta is facing this green. Magenta will remove green from the color. It will remain red and blue. Now, this is yellow. Yellow is directly facing blue. If you have a mixture of red, blue, and green, for example, and you put yellow there, yellow will absorb blue. So, in terms of subtractive or absorption, each of these subtractive colors, they will remove the one that they are facing. Cyan is facing red. So cyan will remove red from primary colors and leave you with green and blue. Yellow will remove blue from primary colors and leave you with red and green. Magenta will remove green from primary colors and leave you with red and blue. Now, what happens? When you add mixing, when you mix red and blue, you get magenta. Red plus blue is equals magenta. When you mix blue and green, you get cyan, like we did here. So B plus G is equals C. When you mix red color and green color, you get yellow. So red plus green is equals red plus green is equals yellow. Red plus green is equals yellow. So far, so good. Look at this carefully and try to revise. Go back. Make sure you understand, because I'm not in a haste. I want you to understand everything. There's what you call chromatic aberration or color fringing. It is the image defect of having blood and color images, and this can be corrected using a doublet lens or double lens. So far, we've started going deep into color mixing by addition, by subtraction. Now, this class will end here, so that in the next episode, we shall go deeper into color mixing to see what happens if some colors are passed through yellow light. What happens and what does not happen, which are basically the hot questions set in most exams. And these areas are the most confusing for students. For that, I am creating a dedicated episode for that, and also question and answer sessions, a lot of question and answers, so that everything about this area is settled for you once and for all. To end this class, these 4 tips are going to help you. With hydrogen lights, the color of hydrogen light is around red. Lines of most colors, even all, are produced. In atomic theory under chemistry, we talked about hydrogen spectrum. How some persons could not explain the lines seen in hydrogen spectrum, while some could explain hydrogen spectrum, but they could not explain the spectrum of other elements. The mercury light produces blue and green lines. Sodium produces yellow lines. And when you are looking at the relationship between linear dispersion and angular dispersion, the L over the lambda is equals the frequency over the theta over the lambda. Sorry, where this is the linear dispersion and this is the angular dispersion. More of that. This class was supposed to cover a lot of things, but I've shifted more of color mixing and questions to the next episode. I've shifted electromagnetic spectrum and spectra to the next 2 episodes. So see you in those episodes. Have a wonderful day.